Alright, hello Physics 30. Today I'm going to show you how to calculate the first two questions on the friction forces worksheet, and I'll try to explain a little bit about the logic behind all these equations up here as well. So hopefully after these two questions you can continue on and work your way through the last questions, the remaining questions. Okay, so the first one is F equals ma. That's just force equals mass times acceleration. That's just a definition of force, and we are using this equation basically again and again in all these friction questions because ultimately we need a friction is due to gravity, and so the force of gravity is basically mass times acceleration. But if we were talking about gravity, then that acceleration is the acceleration of gravity, which is 9.81. So these first three equations actually are just like this equation, F equals ma, is essentially just a general version of Fg equals mg, which is more specific to the force of gravity. And the reason why we use the force of gravity in friction is because it is equal in magnitude to the normal force. And I haven't had a chance to introduce this to you, although the videos should have. And that is that if an object, let's just put an object here, a little box, is sitting on the ground, it'll have a force of gravity on it, just sitting there. There'll be a force of gravity, Fg, and because it's at rest, it means all the forces are in equilibrium, meaning they're all balanced, and so there's actually a force that we call the normal force, and the F subscript n is what we'll use to describe that, and Fn and Fg are equal in magnitude but opposite in direction if it's on a horizontal surface, which all these questions, all the things are on a horizontal surface. As soon as we start going on an angle, like a ramp or something like that, then the normal force is actually always, not always opposite the force of gravity, but it's opposite the, or it's perpendicular to the surface. So let's say we had a ramp like this. Okay, I know it looks like a triangle, but it's a ramp, trust me. We have a block of wood on the ramp. The force of gravity still goes into the earth straight down, but the normal force would actually be on an angle like this. And so on a ramp, the normal force and the force of gravity would not be equal and opposite like this. Okay, so it gets a little more complicated as soon as you go on a ramp. And you probably know that somewhat intuitively, that the friction objects move differently on a ramp as compared to on a surface. If you had a big wooden block on concrete and you pushed along the concrete, it'd be a lot of work. But if the concrete was actually on a big hill, then it'd be easier to push it down the hill. So that has something to do with friction and inclines. Anyway, let's continue on here. The other thing that's new here is we have a coefficients of friction, and there's one for a static, meaning that nothing's moving, and there's a coefficient for when things are moving. And all these things have been determined experimentally. So, you know, so let's say rubber on concrete. So if you moved a rubber block on concrete, you could measure that the coefficient of static friction is 1, and actually as it starts to move, it gets a little bit easier to continue to move because the coefficient of friction drops a little bit to 0.8. And you'll notice in actually almost all these instances that, well, maybe actually all of these do, they drop a little bit. So on ice is 0.1, but as soon as the ice starts moving, it's 0.03, so it's significantly easier to keep it moving. So these are it's just a chart, and you'll also notice there's no unit on these coefficients. There's a few times where you have a unitless number in physics, and this is one of those times, and so you don't write a unit at the end of it because it is unitless. Now up here we have the force of friction is equal to mu, that's the Greek symbol for the coefficient of friction. So just generically, the force of friction is equal to the normal force times, that's Fn, times the coefficient of friction. And these are the two specific equations that we'll use all the time. They're basically the same as this equation, but one is when you're dealing with static force, you're going to take the coefficient of static friction times the normal force, and if you have the if you're looking for the kinetic force, or the force needed to keep it moving, you're going to use the kinetic coefficient of kinetic friction times the normal force. Alright, so let's do a question. I'm going to change to a different color here. Now let's do a question, the very first one. Let's see how well we can do this. And I've done it beforehand so that hopefully the calculations, everything will move quickly. A wooden pallet carries a load of 600 kilogram rest. A wooden pallet carrying a load of 600 kilograms rests on a wooden floor. And then Paul, a forklift driver, decides to push it without lifting it. If the pallet is 50 kilograms, what force must be applied to get the pallet moving? So actually right away we have two masses, and I'm going to call the mass of the load is 600 I missed the decimal point there. Let's put it in 600.0 kilograms. And we have the mass of the pallet itself, so I'm going to call it P, is 50 kilograms. Okay. Now, when Paul pushes the wooden pallet carrying the load, he's pushing both things. So actually, we need to really, these are going to be both together. It's basically one mass. So it's 650.0 kilograms. All right. So hopefully that's kind of a little tricky part right at the start, but hopefully that's not too bad. Now, nothing else seems to be given here. We are asked to find what force must be applied. So we'll write that down. What is the force? And we're asked to get the pallet moving. That means the force that we have to overcome in order to start moving it is the frictional force. So we'll call this one F. Friction, and under a static, so Fs. That's what we're looking for. Now there's actually a couple other things that you could say we know, and that is that it's a wooden pallet on a wooden floor. So we can look at wood on wood and see that this coefficient of static friction is 0.5. So this is mu s is equal to 0.5. And again, it's unitless. And the last thing you're going to find out is that we are going to end up using the acceleration of gravity. We're going to use the force of gravity, and so we're going to need g in gravity. So I'll write it down this time, but I don't think you'd never need to really write this down because it's a given quantity that we all know about. Okay, but it's the case. This will be true for every question. Okay, the gravity is, we're here on Earth and it's 9.81 meters per second squared. And you could say that's the acceleration, but okay, so let's start doing this question. We are looking for F of static friction. And that is equal to, if you look up here, basically you'll just be using this equation or this equation the whole time and then substituting different things into it. So F of S is equal to mu s f of n, and since we are on a flat surface, f of n is equal to f of g, and really if we're being picky we should say the magnitude, because the directions are not the same, so they're not the exact same, but the magnitude, if you put these long lines or you put your variable in between two long lines, this means the magnitude of f of n and the magnitude of f of g, because the direction is not the same. But we're dealing with magnitudes the whole time anyway, so we can just substitute it in. So we can say f of s is equal to mu s f of g. And what does f of g equal? You can see this other equation up here is equal to mg, is equal to the mass times gravity. And so we'll substitute that in, mu S is equal to mg. Just a note, the mu is not a u. It's not a u like this. A mu is, it comes with a line like that before it, and usually it's like a longer line, so mu like that. Something like that. Anyway. Okay. Then we know mu s, we know m, it's MPL, and we know gravity, which is there. So we can just put all those values in. We have 0.500 times the mass, which is 0.0 kilograms, times gravity, which is 9.81 meters per second squared. And all of that, if you multiply it all out, you'll get 3,188.25 newtons. So 3,188.25 newtons, and that actually you're going to round up, or you're going to round because you only have 3 significant digits, so it'll be 3,190 newtons. Okay, and it says what force must be applied to get the pellet to move. So this is the static force. That means if you apply this amount of force to this pellet thing, it will still not be moving, but it'll just be about to move. And so it has to be greater than that. So you might say you must apply more than 390 newtons to get the pellet moving. Yeah. So that's what Paul the forklift driver would have to do. Okay, so that's question 1. I'm going to change my color of ink, and we'll do question 2. So question 2 says Peter pushes a 45 kilogram steel block sitting on a steel floor. So steel block on a steel floor, we'll be looking up here and referencing it up there, that table. If Peter pushes with 300 newtons, will he be able to move the steel block? Alright, let's put down what we're given here. We're given the mass is equal to 45.0 kilograms. And kilograms is the base unit. If something's given in grams, you should convert it to kilograms. It's the base unit for mass. If Peter pushes, and it's steel on steel, so actually we could go mu s. Again, we're seeing if it's going to move, not whether we can keep it moving. So we're still talking about static friction here. And then mu s steel on steel is 0.740. And the force that Peter pushes is, I'll just go F, and I'm going to write in Peter is equal to 300.0 newtons. And so the question is, will he be able to move the steel block? Well, actually, what you're looking for then is the static force. Okay, the force that Peter is, the 300 newtons, that's just what he can push with. That's just his ability. That is not, that has no bearing on the static force that is needed. Okay, it's just, that's what he has to offer. So let's take a look here. We have force of friction is static is equal to mu s Fn. We know from above there that mu s is equal to Fg because we're in a horizontal plane, and mu s is equal to mg. That's what Fg equals. And in this case we have m, we have mu s, and we know g, so we can just put all the numbers in. Again, this is 0.740 times 45 kilograms times 9.81 meters per second squared. Okay, we multiply all that out. And we have 326.673 newtons, which is rounded to 327 newtons. Okay. And the question is, what does this mean? How do we answer this question? Well, this means that in order to move the 45 kilogram steel block that's on the steel floor, we would have to overcome 327 newtons of force just to get it moving. Okay. Now you'll notice that once it is moving, okay, then the coefficient of kinetic friction is actually less, and so the force needed to keep it moving is actually less than this. But in order to move it, we needed 327. Unfortunately, Peter can only push with 300, and so he will not be able to move the block. Okay, so you might say something like, since 300 newtons is less than 327 newtons, Peter will not be able to move the steel block. Okay. So there you go. Those are the first two questions there. I want to just say something. I won't be able to show you here, but I'll just say something if you want to look at the sheet about some of the other questions, because a little bit kind of trick. Well, not too big of a trick. But question 3, it says, what is the difference in force Stephen needs to start pushing a 15.5 kilogram block of rubber on concrete compared to pushing the same rubber block when it's moving? So there you're going to have to calculate the force, a static force, and then calculate the kinetic force separately. And then you want to know what the difference is. So you're going to subtract the smaller one from the larger one. And you're going to notice that the kinetic force is always less, so it's always going to be the static force. Take away the kinetic force and find out what the difference in force is. For question number 4, it says David pushes a block weighing 200 newtons along the surface. Now, we haven't really dealt too much about saying or talking about the weight of something in newtons, but the weight, if something has a weight of, say, 200 newtons, it means that the object has a force due to gravity, downward force of 200 newtons. So that's the force of gravity, actually. So in that question, for question 4, Fg is equal to 200 newtons. And actually, it ends up being that you don't actually have to figure out what the mass of the object is, and you don't even have to use the acceleration of gravity, because all of that's kind of already calculated for Fg. So, question 5. This is just calculating ice on ice, and again you're going to find the static force and then the kinetic force, and you're going to determine if Mary has enough force to be able to push either case, and so you'll talk about that, or you'll make a statement based on the results. And the number 6, this one is just again, what is the smallest force? So here you're trying to just find out what the static force is, and so same sort of thing. Question 7, and then find the static force and then compare it to the person pushing. And then number 7's a little bit more complex in a way. For that one, you have two masses, but they're both attached by a rope, and one that's on the table and then attached to the other one through a rope and pulley that's just hanging there. And so the key here is to recognize that the force, the static force of the box that's on the table is going to be equal to the force of gravity of the second box that's just hanging off the table. So you can ignore the mass of the string for this question and try to figure that out. Anyway, please let me know if you have any questions. Good luck getting these questions done here, and again, let me know if you have any questions through email, or I can also make a video on doing the other questions as well. Talk to you soon.